Hello, this is Tony Nichols, co-founder and Chief Technical Officer of Great Ideaz. And in this tutorial, as part of our enterprise architecture with the data architecture, looking at examples using .NET Blazor, Azure, and Great Ideaz trellispark, we're going to be focused primarily on record storage. So to give you a quick overview, we're going to be looking at what do we mean when we talk about a record and what is data agnostic record storage in this context. We're going to be looking at a couple of common patterns. So we're going to start by looking at command and query responsibility segregation, or CQRS, and we're going to talk a little bit about how some common create, read, update, delete, or CRUD functions are implemented within a data agnostic service. We'll also take the opportunity to have a look at how we can further optimize the query functionality and how we can scale a data agnostic record store. Finally, we're going to consider sustainability in the context of data agnostic record storage. So let's start with the easy stuff. What is a record? A record is simply defined as a specific instance of a concept, or you may be happier using the word entity or thinking about entity. Essentially, a concept defines a class of things that we want to store information about. So for example, a vehicle would be a concept. A concept is going to have one or more data elements. Sometimes you might call them attributes or columns. And an example here is that vehicles may have a make, a model, a year, seating capacity, engine size, etc. Okay, so all of the different elements of data that we want to store about concepts are essentially, sometimes you call them attributes, sometimes you call them columns. Now, an instance then becomes a very specific example of a concept. So my vehicle, if I was creating a record for my vehicle, this instance record would have the attribute make equals Toyota, model equals RAV4, and so on. So an instance is a very specific single example of a concept. So a record for my vehicle would have make Toyota, model RAV4, and so on. So another way you might think about this is in relational tables, we're going to store records in tables with data elements in columns. Okay, so a record essentially becomes an instance, a table is essentially a concept, and the columns are essentially the elements within that table. And in a relational database, every concept and every variation of each concept is going to get its own table and its own set of stored procedures. So for example, if I have a vehicle concept, it would have a vehicle table and a bunch of stored procedures. If I had something that was similar, like for example, commercial vehicle, where I needed to store different information from a personal vehicle, then I would potentially have two separate concepts, two separate tables, and two separate sets of stored procedures. And essentially, a relational database design is also going to enforce a strict set of relationships between those concepts. So if I have, say, for example, a vehicle and then I have a driver and there is a one-to-many relationship between vehicles and drivers, then the primary key of the vehicle might be a foreign key on the driver, or vice versa. Okay, so for example, I might have a driver who can drive many vehicles, and the driver ID would be a foreign key in the vehicles table. Okay, so we talked briefly about record storage as it relates to relational databases. What does diagnostic record storage mean? So essentially what we're talking about with diagnostic record storage is a hybrid approach. We're combining document and relational database principles all in a single database. So essentially what's going to happen is our records are going to be stored as documents using data agnostic XML or JSON formats. And this is great because it allows us to have both the traditional simple database field types like string, number, date, and so on. And it also allows us to introduce complex database field types. So I could have an address, I could have information about an order, and it could all be in one field. Okay, so it's unlimited. So one of the really cool things about XML and JSON formats and data agnostic records is I'm no longer constrained to a set of simple value types that would exist in a column within a standard relational database. I've got the true flexibility or XML and JSON, and I can put any sort of data in there that I want. And one of the really cool things about doing that document storage format using the JSON or XML is that I've now significantly reduced my maintenance overhead on tables. So for example, if I need to add a new column to my vehicles table, if I was doing this in a relational database design, I would have to modify my vehicle table, I'd have to modify all of my stored procs, I'd have to modify all of my business objects, I'd have to modify my user experience, potentially modify the relationships and triggers and stored procs that were all using that vehicle table. With a document storage mechanism like XML or JSON, I don't even need to care about it. I can add an extra couple of columns or an extra couple of elements into my XML. And unless my application needs to be aware of those columns, I don't need to change anything in my application to do anything with them. And I can add and remove fields at will. So, one of the really cool things about data agnostic record storage and the whole movement behind NoSQL and document databases is that we have eliminated now a ton of code and a ton of testing and a ton of problems that we have in relational databases when we're trying to maintain all of this as very structured data with relationships and interrelationships, and then trying to maintain consistency between those tables, columns, and indexes. So this is a really cool thing when we go into document databases. And what this comes down to when we're looking at data agnostic record storage is that we only need a single instances table. And that instances table essentially is going to include a bunch of metadata that describes the record and the record that we're actually going to store. So let's have a look at the instances table in trellispark. So this is the instances table in trellispark. Essentially, every instance or record gets a unique GUID. As well as having a unique GUID, every record also gets a data version, and this will come in handy later when we're looking at archiving and maintaining audit history of data versions of records. So as we go from version 1 of the record to version 2 of the record to version 3 of the record, we can maintain the current data version in the instances table. One thing that we found very useful in trellispark and Great Ideaz is that we also want a human readable instance name field. So that's this column here. And the instance name is useful because if we're displaying a list of instances, it's good for the user, the human user, to actually be able to look at that list and say, well, this is order number 137, and this is order number 135, or this is Tony's car, and this is Susan's car, and this is Rob's car. So actually having a human-generated instance name is quite useful. When it comes to metadata, something else that we really need to do is to be able to describe what sort of record we're actually looking at. So each record, although it has a unique instance GUID, it will also have a concept GUID. So every concept within our trellispark database is also tagged with a concept GUID that tells me what type of information I'm going to encode in my instance data. So here's my instance data field here. You can see that in trellispark we use XML. And essentially the concept GUID tells us how to interpret the XML in the instance data when we're trying to display this record or use this record for something else. So essentially the concept GUID is giving us a context for how do we interpret the instance data. A couple of other fields that we're going to look at later include the hierarchy, the parent GUID, who inserted it, when it was inserted. Another useful field is the current status of the record. So if we have something that has a life cycle, for example, an order, we might want to know whether this record is in its draft state, whether it's been submitted, whether it's been approved, whether it's been fulfilled, whether it's been invoiced, whether it's closed, whether it was cancelled. So actually maintaining a separate field to record the instance status on the instance table, again, is something we found to give us a tremendous benefit when we're building dynamic pages in our user experience. So if you want to understand what all of these fields are used for, then go and have a look at the trellispark Academy information, and there'll be a lot more detail around how all this works. But for this tutorial, what we want to focus on is some of the basic metadata and how we identify a record. So if you're thinking about how we identify the record, the key thing is the instance GUID. Great to be able to track the version of the record we're talking about. This is a read-only human readable name for the instance. This is telling us what type of data we're dealing with. This is giving us the current status of that data. And here is the actual XML fragment that represents the data that we're storing about the instance. So for example, if this was an instance record for a vehicle, all my vehicle information, my make, model, engine size, seating capacity, color, etc., would be encoded into this XML fragment. Okay, so here is a very common architectural pattern that we see in high performance enterprise architectures. And this is the idea of command and query responsibility segregation, or CQRS. So you'll find this CQRS pattern implemented in traditional relational databases, to a certain extent in NoSQL databases, and clearly it also works very nicely in data agnostic hybrid databases. And in each case, the objective of CQRS is to improve performance, scalability, and security of the solution. And essentially it's doing that by segregating the idea of the command and the query. So in traditional SOA services, a command may be something like create customer, create order, process order, invoice order, pay invoice. And essentially the commands are describing the interface functions that are actually creating or modifying data. In data agnostic services and in trellispark, we've abstracted this to simply a save instance or a delete instance. That's it. There's only two options. Either we're saving a new record or we're deleting a record and its child objects. And essentially the command side is going to trigger updates into a set of read-only lookup tables that we are setting up for optimizing the query performance. So on the command side, trellispark is simply having a save instance, delete instance. So if we were going to have a look at the trellispark implementation, you'll see that we have a REST API. The API controller for the instance state controller is very simply getting our instance data. Once we have the instance data, we're going to connect to the database. And then there's a bunch of functions down here that we can do with our instance data. But essentially, we're either going to read an instance out of the database, we're going to save an instance to the database, and this includes both the create and update. And then we can also delete an instance out of the database. And again, as you can see, trellispark, we've got a ton of other functionality associated with our instances. That's part of the REST API data model. And again, you can find information about all of this on the trellispark Academy. But essentially, what we have is a REST API that's encapsulating the core command functions, read, save, and delete of an instance. And then within trellispark, the other thing that we did was we separated out the functionality for the read, save, and delete. So I'm going to do a transfer from this instance state controller here into my read instance. Okay. So one thing that we did within the trellispark is that we separated out the REST API from the actual implementation of the functionality. So if I go here, you can see I have a read instance function. It's an asynchronous task. And what it's going to do is it's going to basically get session user instance information, the required version, and it's going to go into the database and actually read the instance out of the database and return the appropriate data to my users. And as you can see, this is quite complex functionality involved in this, and this is mostly associated with our dynamic page generation that we use to reduce the user experience costs of building out new applications. The other thing that we did when we implemented trellispark is that we built an interface for the database here in a separate REST database class library. And then we built implementations. So far we built an implementation for Microsoft SQL Server, but in the future we could also add additional implementations for things like MySQL, Progress, Oracle, IBM, DB2, whatever, okay? So the idea is that by hiding the implementation of the record storage behind an interface, we can then import new implementations into our models to support new technologies into the future. So if somebody really wants a MySQL implementation as opposed to using Microsoft SQL Server, all we really have to do is replace this MS SQL Server implementation with an equivalent one for MySQL. So we've talked a little bit about the command size of CQRS. So essentially what we're going to do is we're going to optimize the processing of save and deletes so that we are only updating our instances table. And then we're going to put a trigger on that instances table to update a set of read-only lookup tables that we're then going to use to optimize the performance of queries. So the other side of CQRS is obviously the query side. So on the query side, what we want is the ability to do an optimized search over a set of index lookup tables. Essentially, the query side is how do you find the records that you want to present to the user? And the point of separating the command and the query is that the way we want to store and maintain data is not the same data model as the model that we actually want to present for query. Okay, so if we want to do highly optimized search over complex joins, the data model that we're going to build for that can be very different to the data model that we're creating to actually save the information. So what we're going to have a look at in this presentation is different ways where we're going to use code generation to actually optimize the query functionality to search index lookup tables. And essentially, once we have executed the queries and now we want to pull the record back and present it in a user interface, then we're going to use that read instance function we were looking at in the C# a minute ago. So what we've got is we've got the best of both worlds in our hybrid database solution. On the command side, by using XML, we've got all of the benefits of a document database. And on the query side, we've also got all of the benefits of using a relational database and being able to optimize those queries using indexes, lookup tables, and all sorts of really cool technology that we've just been taking for granted now in relational databases for the last 30 odd years. So essentially, it's a hybrid. It gives us the best of both document and relational databases. So one of the cool things we do in trellispark is we look at the best use of code generation. So one thing that we've done is we've done a bunch of code generation to deal with the CQRS T-SQL. So essentially what we're trying to do is on the CQRS side, on the command side, whenever somebody comes along and either inserts or updates or deletes a record, we want to actually fire a trigger. So let's have a quick look at what that will look like. So here, if I have a look at my instances table and look at the available triggers on the instances table, you see I've got a trigger here called maintain lookups. Okay, so my maintain lookups trigger is going to centralize anything related to the insert, update, or delete of any instance record in my database. So there's a bunch of stuff that this is going to do for me. First of all, if I delete a record from my database, I want to be able to delete the record from all of the lookup tables. And I can do that by calling this lookup delete function. And then if I'm inserting a record into the instances table, I can have another cursor that's going to go around and do the lookup insert. So what this is going to do is it's going to say, well, Tony's got a vehicle called Tony's vehicle. When it's initially created, I just need to call the lookup insert for the vehicle in version 1. And then if version 2 comes along, I'm going to tell it to delete the version 1 lookup information and replace it with version 2 lookup information. Okay, so really simple, okay, is whenever we make a change to the vehicle record in the instances table, we're going to remove and update the information relating to that vehicle in the lookup table. Now, not every single concept type needs a lookup. Okay, so one of the things that we're doing inside our code generation technology is we're indicating which of the concepts within our data model will require lookup, and do we want to include all of the fields in the lookup table or a subset of them. So again, this is our first pass at optimizing which fields we're actually going to pull across. So one thing that we're going to do here inside our lookup insert, so here is our lookup insert pass, is we can use this as a great place for tagging a bunch of information and a bunch of functionality related to actually processing records. So again, covered in detail in the trellispark Academy. And essentially what we're going to be doing here is looking at how we then go ahead and code generate some of this functionality. So essentially what's happening is when I update an instance in my instances table, I'm going to quickly run through and see whether or not I've got any functionality in our lookup insert save functionality for this particular concept. So inside here, I could come in here and I can scroll down here. And again, we talked about the concept ID being key. This is telling us how to interpret the data. So if I scroll down to here, for example, I can see that if the concept GUID equals this value here, then I'm going to update the lookup information for a client. So our code generation is going to generate this code here. And it's also then going to generate the equivalent lookup save functionality for our client. And you can see what it's doing here is we're going to auto-generate a lookup ZGI client table using our data model. It will have all of these fields that we've identified here. And then what we want to do is we want to shred the XML to use these values from the XML to actually populate the fields in the lookup table. So this is a brilliant use for what code generation is all about. Code generation, if you think about it, you can't build anything more complex with a code generator than the code generator itself, right? Because if you want it to execute some logic, if you want it to, have some functionality or ways of implementing select statements or if statements or exception handlers, if you want to have that inside a code generator, then you need to be passing that information in there so it knows at this point you want an if statement or a switch statement. But if all you're going to do is use it to generate very simple logical blocks like an insert statement into a lookup table, code generation is perfect for that. So this is a great way of using code generation to save yourself typing a bunch of boring code. And the other nice thing about it is if we ever change the definition of a client to add some extra columns or extra fields, it's very easy for us to just take the code generator and regenerate this, right? There's no complexity. There's nothing I should be customizing behind the scenes here. Essentially, the code generation is producing the current version of the lookup select for a ZGI client without us having to worry about somebody coming along and customizing this function later. Okay, so we talked a little bit about putting a trigger on the instances table for the insert, update, delete, and using code generation technologies to power all of that. And we talked also about how those updates are keyed off the concept GUID. Now, the other thing that's really cool with this as well, right, is that as well as using this to maintain the lookup tables at the highest level, so client concept has a client lookup table, if you've got a much more complex data model where you may have to say be doing multiple queries, sort of like including say 3 or 4 or 10 different lookup tables, the other thing we can do is maintain second level and third level lookup tables that summarize those joins. Okay, so that whenever we update an instance, as well as updating potentially a first level lookup table using our code generation, we can also use that to go and update second and third level lookup tables to mimic the joins. So the thing to think about there is it's great if you've got a bunch of complex joins, but you only really want to use this technique where essentially there are lots of reads, lots of queries that are being performed on those joined operations with relatively few updates to the records that are going to change them. So if you're querying far more than you're writing, then actually having secondary and third level and possibly even fourth level lookup tables would be a good idea. And certainly we've seen implementations where we've gone down 3 levels of a lookup table to really optimize the performance on very complex joins. The other thing, this idea of using the trigger on the instance table, is that it gives us a great hook for calling any custom T-SQL whenever an instance is created, updated, and potentially even removed. So one of the things that we do within trellispark is that within our instances, we can also say for this particular concept, if you are inserting version 1 of a particular instance, call this store procedure. If you're inserting version 2 or above of this instance, then call this other store procedure. So one of the really cool things is essentially being able to use this as a hook for whenever we want to create, update, and potentially even delete a record out of the database. The other thing that we do within the trigger is provide an outbound data flow, a point where we can synchronize information. So whenever we go in and change an instance within our instances table, we can also trigger an outbound flow through a message queue or through an instance changes table that we can then use as a mechanism for synchronizing changes from our instances table to other solutions. And essentially what this enables us to build is a really effective entity synchronization layer. So when we were looking at our instances table, you would have noticed 2 other fields in instances, a parent GUID and a hierarchy. So one of the most common relationships that is really meaningful within a relational database is essentially a parent-child hierarchy. So for example, a parent could be, let's say, a customer, and then within a customer, I might have an order. Within an order, I might have an invoice, an order line, and under an order line, I may have some information about pick, pack, shipping information. So essentially, there is a relationship between parents and children. So if you look at the diagram over here on the right-hand side, you'll see I've got an instance record A. It contains instance records B and C, and that record C has a child instance D and a child instance E. So one of the things that we've done to make it really quick to be able to do searches on the instances table themselves is we've added fields for both the parent GUID and the hierarchy. So if we look at record E, then the parent GUID of E is D. And the hierarchy of E is A, C, D. Okay, so 2 different ways, if we look at our instances table. So 2 different ways in our instances table of representing hierarchy. So we have absolute hierarchy from the root of the object into the workspace and then down through the workspace to all of the instances that were parents of this, and then the immediate parent GUID of the record immediately above it. And this gives us tons of optimized capabilities when it comes down to querying nested sets of records, and it also enables us to be able to very effectively identify records that are targeted by deletions. So for example, if I want to delete a customer, I better know everything that sits underneath the customer, because if I remove that customer record, all of its child objects now no longer have a parent. Okay, so that's parent-child relationships. What about where, let's say, D wants to reference B? Okay, so this is really simple. All we do is we have a field in the XML fragment for D that contains an element that references B. Okay, so bear in mind, okay, our record XML fragments can contain anything. So they can contain references to any other record in the instance hierarchy. And indeed, one of the really cool things about XML is it may contain references to multiple B-type records as well, right? You have no limitations or restrictions. It's XML. You can put into the XML whatever you want. Okay, so when we're dealing with relationships within the data model, we have even more flexibility than we would in a normal relational database because we have the full capability of XML to play with here. So we touched a little while on the idea of version history. So we said that when we're looking at an instance record, as well as having an instance GUID, every instance record also has a data version. So let's go and have a look at that again. So here is our instance record. It has an instance GUID, and that in the instances table is the primary key of the instances table. Every record gets its own instance GUID. Part of the metadata for the record is this data version, and this is an integer incrementing from 1. So the first version of the record is always version 1, and then we create version 2, version 3, version 4, and so on. Now, when we create the record and create its first version, we also want to know when it was created and who created it. So we have created on fields and created by GUID fields. So the created by GUID would be the user GUID of the user who created the record. And then every time we add a new version, we're going to update the inserted on and inserted by record fields to indicate who actually put in version 2, version 3, version 4. And again, one of the really cool things about data agnostic services is that means we only need one instance history table. And this instance history table essentially looks very similar to the instances table. And essentially what this is enabling us to do is maintain version 1, 2, 3, 4, 5 of the instance record over time. So this gives us a full audit history. We can look from when the record was created right the way through to the current date and time, and we can see all of the versions of the instance data and who modified them. So this gives us really cool audit trails. And the way that is maintained is obviously through our maintain trigger. So here you can see the code that we use to maintain the instance history. So all we have to do to maintain the instance history is make sure that we're not writing another copy of the instance GUID and data version. Okay, so essentially here, we're checking to make sure that we're not trying to overwrite the same version of the same instance. So this should always be essentially a null check, right? Whenever we do this, if I'm going to insert version 3 into the instance history, version 3 shouldn't already exist, right? We should only be inserting version 3 if there is no version 3. So one thing that we found is it's always a good idea to be absolutely certain so you never get this duplicate key on entry. But what we want to do is we then want to write into the instance history all of the useful information out of the initial instances table. So you can see in instance history, our primary key contains both the instance GUID and the data version. And this is cool, right? Because think about what we've achieved here, right? We have now got instance history on every version of every type of record in the database, and we've only implemented two tables, an instances table and an instance history table. And again, this is one of the really cool things about using document storage rather than a relational database. So if I was doing a traditional relational database and I had a table for a customer, a table for an order, a table for an order line, a table for some of my fulfillment data, and I wanted audit tracking on that, I would have a history table for my customer, a history table for my order, a history table for my order line, history table for my fulfillment information, and I would need separate sets of code to maintain the copying of attributes from my customer to my customer history, my order to my order history, and so on. And if I needed to change my customer columns, I would now need to change my customer history table and all of the code that's basically maintaining it. Here, again, this is the beauty of data agnostic services and using this XML format. We have implemented history for every type of record in the database, and we did it in a couple of statements. Now, by default, we maintain the version history of every instance of every record in the database. But one thing we've also recognized is that we need to be able to purge history records for selective concepts. So, for example, I might not need information about fulfillment data 3 years after we fulfilled it. So what I can do is I can then execute a purge of history records on selected concepts if it's not required. And I can set a date to say, well, okay, keep this forever, keep this for 7 years, keep this for 6 months. And again, it's a simple update statement, right? I'm just going into the database and saying if the concept GUID is this and the date of the record is, over 6 months old, delete it. So you can see, right, the whole point of using this data agnostic storage is we're really simplifying a ton of complex functionality that would be hard to implement in a relational database. We really are chewing up and throwing away 95% plus of the CRUD code that we would otherwise have to write. So another thing we've talked about is securing individual records. So when we're thinking about security and privacy for our data agnostic record storage, we want to build in security by design. And ideally, the best granularity of security that we could have on our record is row level security. So if I've got a list of 1 million customers and Tony is only allowed to update 10,000 of them or to see 10,000 of them, I don't want Tony to see the whole customers table. I want Tony to just be able to access the 10,000 records that Tony is allowed to see. So security and privacy are now prerequisites in any builds that we do. And essentially, I think about it this way, right? Users are people who need to see data, and groups are a way of actually adding multiple users to the same group, so everybody in this group can see the same set of data. So for example, Tony may be in the GTA, and he's supposed to be able to see GTA customers, but he's not allowed to see EU customers. Okay, so I would add Tony to the GTA group and then give the GTA group access to see the GTA customers. So security is granted to sets of users and groups. Now, for Tony to be able to see a record, I must be explicitly granted access to see that record data. Okay, so what I now need is a way of actually securing individual records. So let's go and have a look at how we did that in trellispark. So what we did, and you'll see this is just a recurring pattern, is we added a table called instance access with two columns, an instance GUID and a user group GUID. And the rule is simply this. if I want to access an instance record, I need an explicit recorded instance access that says that Tony is able to see this record directly, or is able to see this record because he's in a group that can see the record. So every single record in the database essentially is locked to an individual set of users that can actually see that record. Okay, now think about that for a minute. If I did that on every single record in the database, I would have more instance access records than I've got instances, and querying it to determine whether Tony can see a particular instance becomes an issue in and of itself. So we can actually make some interesting simplifying assumptions. So let's go and have a look at what those assumptions are. So if you think about our previous slides, we have this idea of an instance hierarchy. So the first simplifying assumption is that to view any record, A through E, Tony must have access to the record A through E, one way or another. Now, the way it works is we use a cascaded access permission. So essentially, let's say the access rights are granted on record A. If Tony has access to record A, then by default, Tony has access to records B through E, unless specifically overridden. So if records B through E do not have any access rights on them at all, and Tony's trying to access record E, then we navigate back up the hierarchy. So there's no access records here, have a look here, have a look here, have a look here. Oh, there's an access record on A. Tony has access to record A, therefore Tony can see record E. And this then is a really simple test, right, when you think about it. So let's say, for example, Tony has access to record A, but I shouldn't see record D. So if record D has had an access override so that Tony does not have access to record D, and I'm here on record E, I go, can I see record E? I don't know, have a look at access rights for D. Can I see record D? No, there are access rights here, but Tony doesn't have access to D. So in that case, what we're going to do is prevent Tony from seeing D or E. Essentially, those records are hidden, even though Tony has access rights to C and A. So this is really simple, right? Because what it means is that with three tables, an instances table, an instance history table, and an instance access table, I've immediately got, I can save any sort of data, I can maintain a version history of any sort of data, and I can maintain row-level access for individual users against any subset of that data. And this focus of data agnostic services on relatively few functions means that it's then easy to add additional security features and other CRUD plus functions. So for example, if I wanted to add audit, so if anybody reads a record, I want to have an audit record to say that Tony read this customer at this date and time, I've only got to put that code into one place. I can go into my read instance stored procedure, and I can say, as part of reading and validating the fact that Tony had access to this record, Tony read this record at this date and time, or Tony was denied access to this record at this date and time. Okay, so you can see there's only one point in the entire database for me to actually put that piece of code. It makes it really easy to add that security feature if I need it in any particular application. The other thing it allows us to do, for example, in medical healthcare scenarios, is enable us to provide a break the glass override. So Tony tries to access this patient record. Normally, he should not have access to that patient's record, but Tony might break the glass and obtain access to that record in an emergency, but the mere fact that Tony did that then flags a whole bunch of audit alerts and triggers to say, well, Tony actually broke the glass on this particular record. Was he right to do so? So again, if we want to put some additional security features inside our UX to allow us to break the glass and access records that we're not allowed to access, then again, we have one point where we can establish that code, and that gives us, again, a really centralized point where we can add additional functionality into the solution as a whole. So far, we've talked about creating and updating records, and we've talked about querying and reading those records. But what happens when we want to delete the records? Is there anything else we can do that's really cool with data agnostic record storage? And the answer is absolutely. So one thing that we've again found really useful in Great Ideaz in our trellispark implementation is this idea of a virtual deletion strategy. So sometimes, if you think about it, users delete things that they shouldn't, and they come back to you sort of like a few weeks or a few days or 10 minutes later and go, I just deleted this customer. It was a really big customer. I really made a big mistake. Can you recover it? And if all you've got is a relational database, sometimes it can be really hard to do that, right? So one of the really cool options here with functionality in trellispark is that we don't do physical removal of records. So what we do instead is we start in this blue layer here. These are the real records that are currently visible to users. And when a user submits a record deletion, we get one of these delete requests. So essentially the delete request, assuming that the user is actually allowed to delete the record, actually just moves the instance data from the blue into the green, into the deleted instance record tables instead. So this means that we now have a copy of the record, its access control, and all its audit history in a set of mirror tables, so they're not impacting the performance of the user experience. It's clear which records are current, which records are deleted. And what this enables us to do is a whole ton of really cool functionality. So for example, if I want to delete a customer, but 5 levels down in the customer hierarchy, there's some records here that are still active, which means I shouldn't be able to delete my customer. My validation request should say, well, Tony wants to delete this customer. Go and check the customer and all of its child objects to make sure that Tony is able to delete them at this time. And if Tony isn't able to delete that customer at that time, because one of these records in the lower levels is still open, then I can prevent the entire deletion operation, just roll that request back. On the other hand, if Tony is allowed to delete it, then I can move the entire object hierarchy of that customer from the active tables to the passive tables in one transaction. Now, what this enables me to do is then say, well, Tony made a mistake. He deleted a customer. He shouldn't. Can you please restore that customer? So what I can do is I can now go to my deleted tables and use the request ID on the deletion to say Tony now needs to actually restore this customer. And then in one transaction, I can move all of that deleted instance data, history data, and access data back into the active tables immediately. So this is a really cool idea on virtual deletion. It enables us to deal with the mistakes that users make on a day-to-day basis, and it also means that we've persisted the audit trail on financial records, even if the user actually tries to remove the records. So we know which user tried to remove them, what version history of all of those records were, and essentially we've got it all between 2 sets of tables. So in total, if you think about it, we're up to 6 tables. Okay, an instances table that can hold anything, an instance history table that holds the version history of anything, and an instance access table that gives us row level access control to anything, and then 3 mirror tables that says these records have been marked for deletion. So this is great. I mean, we've already made some huge optimizations and we've really cut down the amount of code that we're producing, but can it go further? And the answer is yes. I mean, again, we've had trellispark customers where we've really needed to optimize further the query functions. So one of the things that we found really useful as an implementation was the ability to create and maintain reporting databases. So we've already got this maintain lookups table, okay? And what we want to be able to do is if we've got a bunch of really complex queries or reports or analytics tasks, ideally, I don't want to run those on my production servers, and my production database server that's powering my user experience. I would like to be able to take those queries and push them off onto another database, ideally on another database server. So essentially what we're going to do is we're going to use that instances trigger that we talked about in a couple of different ways. So again, we've implemented this 2 ways ourselves, and there's potentially a whole bunch of other options here, right? So in one case, we added an instance changes table into the maintain lookups. So whenever you updated certain concept types, we write the changes to the instance changes table, and then we have either a push or pull into a decoupled reporting database. So essentially, the changes were buffered internally within the UX database, and then were picked up either as a direct push or a pull from a reporting database, and then those push or pulls were happening, every few seconds. So we had an almost real-time synchronization of the UX primary data against the reporting tables. And for the reports that we were producing, that was perfectly adequate. As long as it was good to within 24 hours, that was fine. We were good to within a few seconds, typically a minute or two. So that was effective in and of itself. The other scenario that we've entertained in the past is instead of writing it into a local table and then pushing and pulling the table contents into the reporting database, is that we've actually written the instance record into a queue, into a message queue or an enterprise service bus, and then the reporting database has had a service that's pulled data out of those message queues or ESBs into the reporting database. So that tends to be more decoupling than I typically like and a bit longer latency. But again, for certain workloads, that's fine. Right? It works perfectly. So the reason that we're doing this, obviously, is that by taking the data almost in real time out into a reporting database, we can then optimize what's going on in that reporting database even further, right? So we can have more decoupled queries, we can put more indexes on there, and then we can run complex reports and analytics on this real-time clone of the instance data in a reporting database without impacting the core performance of the user experience database. The other thing that we've used this for is to execute the request, the complex query on the reporting database, and then return a list of instance GUIDs to our primary UX database to actually display them. So again, you need to be aware of the latency, but in many scenarios, the latency is acceptable depending on how you're actually pushing the changes from the primary core UX database into a reporting database. So again, this whole thing, the data agnostic storage and the ability to actually tag through one trigger on the instances table, all of this functionality gives you tons of ways to actually optimize how your solution is actually going to work in real time. So another question I commonly get with this, well, how do you scale this, right? If you want to run this database and you're going to put like hundreds of millions, thousands of millions, tens of thousands of millions of record into the instances table, doesn't it get slow? The answer is actually no, it doesn't. We've been running this with relatively small infrastructure with very large numbers of records into the hundreds of millions, going on to the thousands of millions of records, and essentially getting sub-second UX performance out of these databases. But even saying that, if we actually got to a point where we needed to scale horizontally, think about this, right? If I had a traditional relational database where I've got maybe 1,000 tables with complex insurance policy information on, and I needed to scale that across 2 database servers, and now I've got to pull apart 1,000 tables and all of the relationships and move 500 of them into server A, 500 of them into server B, and that is like really complex to do and maintain the relations and then all of the other stored procs and everything else, right? It's a real mess. Splitting and scaling relational databases, I mean, I've been there, I've done that, I really hated it. Was not pretty at all, okay? On the other hand, scaling data agnostic storage is really simple, right? Because I can partition my instance table across multiple file groups and disks if I'm just trying to get IOPS performance in a single physical or VM environment. And I can also move multiple databases across different database servers. Okay, and it's really simple, right? Because all I'm going to do is partition my instance table. So from my external interface, I can say if the concept GUID on this record is in the range A, then move it into the upper database A, and if it's in the range B, then put it in database B. Okay, and that's it. And if I need to split a bunch of concepts from one database into 2 databases, all I'm going to do is take my instances table and say, take all the concepts with this range of concept GUIDs and put them over here, right? And it's really easy for me to split them out that way, okay? It's a trivial function to split my database that way. And then because my data agnostic record storage is all hidden behind an external interface, right, and that implementation is totally hidden and invisible to the user, that means the user isn't aware of how many databases or servers that I've had to scale this database out to. So if I now need to add a 3rd database server on here, I can do that internally and the user wouldn't even know that I'd moved it. Okay, and by the user in this case, I mean any client that's trying to connect and save data. Because as far as the client is concerned, they're calling save instance, delete instance, read instance, and the fact that it's in database A, B, or C is completely irrelevant and hidden from that user. So I've got, say, a bunch of websites tagged to this storage, maybe a bunch of mobile applications tagged to the storage, thousands of workflows tagged to this storage, and if I now need to execute a scaling update, then I don't need to worry about any of those other things. All I need to do is correctly implement the scaling solution, test the external interface out, and there you go, job done, finished. Okay, the scaling occurred completely in the implementation and behind the external interface. The other cool thing here, obviously, as well, is that I can completely change the technology. So within Great Ideaz, our preference is Microsoft SQL Server. Okay, but within another organization, it may be MySQL or Progress or Oracle. Pick your database technology of choice. All I need to do is re-implement the database client that I showed you earlier to change from one database format to a different database format. And again, none of the services in data presentation, data in motion, data in action are aware or care. Right? So this is really cool. Hiding the implementation gives us ultimate flexibility on scaling and technology. The other really cool thing is, again, it's all hidden behind that external interface. It's all triggered off that maintain trigger that we talked about earlier. So that means that I can put my lookup tables and indexes anywhere. They can be in the database. I can just have one database that's powering everything, or I may have several databases, and I may have a database particularly customized for maintaining a query that's joining 13 separate tables somewhere else, right? And I can maintain that as a completely separate data store. I can deal with all of the performance issues relating to that database, and it can be completely separate from the core database where all of my updates are actually being focused. So this means I can have maximum performance from my user experience and my workflows and stuff, and also have maximum capability of optimizing the queries and the analytics on that data without impacting my user experience database. So one word that's common in architecture right now is sustainability. And how does this impact sustainability? Well, within Great Ideaz, we think about sustainability in a slightly different way than most people. So we're thinking about sustainability primarily from the life cycle of the application as a whole. So this application may be running for decades, right? And it's quite likely that over the course of decades, the business requirements are going to change. They're going to want to add and remove fields. Well, in data agnostic storage, it's just XML. Add and remove fields as you want. It doesn't make any difference to me. If you want to add an extra 3 fields into your XML through your user experience, then that's great. You can do that. It doesn't impact the data modeling. It doesn't really impact anything that's going on. The only time I even need to be aware is if you want to include those extra fields in a lookup table, in which case we're just going to use the code generator to generate the T-SQL that's going to update that lookup table. Easy. Okay, and that applies to whole concepts. So I might start off with a concept called vehicle, and at some point in the future, I might want to add a new concept called commercial vehicle. Okay, so I can add a whole new concept of commercial vehicle, and I've got personal vehicle, and I've got customer, and customer can have child objects of either personal vehicle or commercial vehicle. That's great. I changed my UX to say, well, the person can have commercial vehicles and here's commercial vehicles, and everything works. But all of, say, for example, insurance policy information may be the same under personal vehicle and commercial vehicle, and I can just reuse it. Right? I can just say, well, okay, I've got customer, I've now got this new concept of commercial vehicle, and I'm going to reuse all of my insurance concepts that I had already built for personal vehicle. I'm just going to drop them under commercial vehicle, and they will work just as well. I don't need to worry about in a relational database whether I've got a foreign key relationship between the personal vehicle and the insurance policy. Now I've got commercial vehicle. How does that foreign key work if I want to reuse insurance policies under my commercial vehicle in a data agnostic storage? It doesn't care. Right? So this is really cool. So this is an example, for example, of using insurance policy, the same concept in multiple places, but still maintaining the relationships between the parents and child as we're actually building stuff out. One of the other things that we've talked about is essentially extending CRUD, the create, read, update, delete functionality to CRUD Plus. So again, if you go and have a look in our trellispark Academy, you'll see how we've extended this idea of instances to also track state transition diagrams for the instances, to track workflow for the instances, to track milestones against instances, events, and so on. So it's really easy to modify the core database to include additional functionality over and above the baseline CRUD functionality. And again, if you go and have a look at the trellispark Academy, you'll see a bunch of ideas and implementations that we've already executed to do this sort of thing. We touched about it earlier in the presentation. Because we implemented the database as an interface, and then we provided an implementation specific for Microsoft SQL Server, we can change the underlying database storage technology completely, just by rewriting the implementation of the interface. And then none of the code that lives above our REST API is then actually impacted by that. So essentially, this gives us a really cool way of decoupling the actual implementation of the fact that we have data agnostic record storage from the interface to that storage. And then to take a more greener idea of sustainability, one of the things that we have found time and time again as we've implemented data agnostic record storage is that the efficiency gains that you get by using data agnostic record storage means that typically you need significantly less infrastructure to host the record storage. So when you're looking at the underlying implementation of how easy it is to add new instances to the instances table, okay, think about it. Those are always like single record inserts using a primary key. Right, when you're actually indexing and cross-referencing that information, because you're pulling that out potentially into a bunch of read-only lookup tables, you don't have to store the whole width of the table. You can just store the columns you need and then index the hell out of that, so that it makes it very, very efficient for your storage media to actually return the results of the query, so that you can do that. And you can obviously put it onto other servers as well if you need to. But one of the main things that we've seen is that you can actually host quite extensive enterprises on a small SQL Server platform and get some great results from efficiency. So this architectural approach is also green in the sense of less infrastructure footprint means less environmental damage, right? Less carbon dioxide and stuff. Okay, but when you actually sort of think about sustainability for the life cycle of an application, these other points, right? The ability to change your data model to add or remove concepts and the relationships and so on, is going to save you a ton of time, a ton of pain, and a ton of cost in actually maintaining the operation of the database over time. And it also gives you then the option of being able to grow your business, because given that you aren't tied down to an implementation in a relational database, this whole benefit of being fast and easy to upgrade means that you can take advantages of business opportunities at a lot lower cost and risk and get to market faster.
To learn more about Great Ideaz products and solutions, visit greatideaz.com. That's Great Ideaz with a Z.com. Thanks.